Stan Gibilisco here. I would just like to explain to you, as the WSJT amateur radio signals grace the audio background, and you're looking at the Long Wave Ranch near Cody, Wyoming, amateur radio paradise. On my computer wallpaper, took that photo with an iPad. It's a 2-acre property out there in Cody, Wyoming, with nothing to the southeast but undevelopable canyon. Great for kite antennas, balloon antennas, but I don't live there right now, not yet. Anyhow, what I'd like to do is start out just by showing you a simple model, a simple diagram of what they call the Bohr atom, B-O-H-R, named after Niels Bohr, the physicist who first dreamed up the idea that electrons, negatively charged particles, could orbit the nucleus, positively charged, of an atom. Nucleus clumped together kind of like a raisin muffin. The little black things there represent protons with a unit positive charge, and the little gray dots here are the electrons with a unit negative charge, and the little white dots are neutrons with no charge at all, and the idea is that these electrons orbit around that nucleus. They're held in orbit by the attractive force between the negative electrons and the positive nucleus. So that's the basic concept of the atom, and if you have a whole lot of these atoms and you have a certain substance that's a solid like copper or aluminum, where the electrons here in the outer orbit can easily get stripped away, then an electromotive force, a voltage, a potential, can cause those electrons to migrate from atom to atom. They sort of jump from atom to atom like this. Here are two adjacent atoms. Their dashed lines represent the orbits of the electrons. The little raisin cakes in the center are the nuclei, and an electron can be pushed or motivated. That's where the term electromotive force goes. It motivates a current to flow by causing electrons to migrate from atom to atom, from the more negative pole, which would be off to the left here, to the more positive pole, which would be off to the right. So you can imagine connecting a battery's negative pole over here somewhere to the left, a positive pole over here somewhere to the right. You get these electrons flowing, and if you get enough of them flowing, as I've outlined in a previous video, if you get a coulomb, or 6.24 times 10 to the 18th of these things moving past any given point per second in the substance, then you have a current of 1 ampere. Well, there's another kind of charge carrier that can move in some kind of substances, notably certain semiconducting materials. And those are electron vacancies, or places in an atom where an electron should be but isn't. And they call those holes. And I've diagrammed here sort of the way that works. Here's the electron actually jumping from one atom to the next. And then these holes, which are not really objects at all, each time an electron moves like this, then in theory, this conceptual object, this nebulous thingy called a hole, kind of like an empty seat in a theater or something like that, moves back that way. This hole is now gone from this atom because the electron has come in, and it appears over here in this atom because the electron has just departed. So that is how hole motion works. And so if you hear the term hole in regards to semiconductor materials, you know that a hole is actually an electron vacancy, and as such, it has a positive charge in effect. You might say, in effect, a positive charge. So the negative charges in this diagram would flow from left to right. The positive charge would flow, in quotes, from right to left. So that is how hole motion works. You'll find all of this information, by the way, in Chapter 1 of my book, Teach Yourself Electricity and Electronics, 5th edition, a link to which I will provide in the description of this video. Until next time, back to the Long Wave Ranch, where communications will someday be carried out on the long wave frequencies. That's where I got the name for it from. Until next time, so long.